Adversary path analysis is the basic technique used to analyze the security system, and in these slides we'll describe how to analyze a single direct path. In the big picture of the depot methodology, single path analysis is a technique used to analyze the physical protection systems design. Earlier in this course, we explained that the depot process is based on performance data and that the probability of attack is not a measurable value. We will now make a substitution into the risk equation and define the effectiveness of the security system, P sub E, as the product of the probability of interruption, P sub I, and the probability of neutralization, P sub N. The probability of neutralization was described in the previous section and is the probability that the adversary is neutralized, given that they are interrupted. To calculate risk, we therefore need to be able to calculate the probability that the adversary is interrupted. We calculate the probability of interruption by employing pathways analysis. Pathways analysis requires the adversary to traverse a specific path from a starting point, which is typically off-site, to a target on-site. The path is made up of a set of tasks that the adversary must complete to reach the target. Each task can be assigned an amount of time and a probability of detection based on detection and delay characteristics of the protection system, as well as the characteristics of the adversary, which are defined in the design basis threat. Before we get into analyzing pathways, we will need to define some commonly used terms. The first is timely detection, which refers to detection that occurs early enough along an adversary's path so that the remaining adversary task time is greater than the time it takes for the response force to respond. Another term is a critical detection point, called the CDP, which represents the last element along the adversary's path where timely detection can occur. Finally, we'll define the probability of interruption as the accumulation of timely detection probabilities along a path. Calculating the probability of interruption is similar to calculating the total detection probability of multiple complementary sensors. We will use the non-detection probability of each detection point before the critical detection point for the probability that the adversary is not detected at each of those points. We can then multiply all of these together to get the probability that the adversary is not detected up to the CDP, the critical detection point. Detection after the CDP is not included, since the response force would not have enough time to respond to alarms at these sensors. The probability of interruption, which is the probability that the adversary is detected before the CDP, is then simply 1 minus this value. Now we will go through an example pathway to demonstrate how to calculate the probability of interruption. In the table, you can see a list of tasks with their associated task times and detection probabilities. In the middle column, we have the total amount of time remaining for the adversary to complete their attack after they complete each task. The first step is to define the critical detection point. For this, we will need the response force time, also called the RFT, which we see from this example has a value of 200 seconds. If you look at the time delay remaining column, you will notice that after penetrating the wall, only 105 seconds remain in the adversary's attack path. This means that if the adversary is not detected before completing this task, the response force will not be able to respond in time to stop him. The last point of timely detection is, therefore, before the adversary reaches the wall. We can now determine the probability of interruption using the non-detection probabilities for the first 4 tasks. The calculation is shown under the table and yields a total non-detection probability of 0.28812. The probability of interruption is just the inverse of this and is thus 0.712. This means that the guard force has a 71.2% chance of interrupting the adversary if the adversary chooses to take this path. On the next few slides, we'll change some of the parameters of the protection system and show how this affects the probability of interruption. In this table, we have the same pathway, but have added an improved detector to the outer door. This does not affect delay times and thus has no effect on the critical detection point, but it changes the non-detection probability to 0.1729. Thus, the detector upgrade has improved the probability of interruption from 0.712 to 0.827. In this table, we again have the original pathway, but this time we've added protection at the pump, which has increased delay from 35 seconds to 140 seconds. If we take a look at the time delay remaining column, we see that this changes the critical detection point to a point before the adversary runs to the inner door. As a result, the detection elements up to this point are included in the interruption probability, which changes the non-detection probability to 0.0706 and the probability of interruption to 0.929. Here again we have the original pathway and have improved the response force time from 200 seconds to 80 seconds. Similarly to increasing the delay at the pump, this shifts the critical detection point to before the inner door is breached and gives us the same result as the previous example because we're now including all of the detectors until the CDP. In summary, the probability of interruption is used to determine the effectiveness of the security system, along with the probability of neutralization. We quantify it using detection and delay elements of the security system, as well as the characteristics in the design basis threat. The probability of interruption can be improved in a number of ways: by adding or improving detection before the CDP, by increasing delay after the CDP, or by decreasing the time it takes for the response force to respond. The analysis technique presented here analyzed a single pathway. For a facility, there are a number of possible pathways that must be analyzed simultaneously. The technique for doing this will be introduced in the next section. However, the pathway analysis techniques presented here are also the basis for those used when analyzing multiple paths.